So, we talked about a very useful device known as transistor, in which you diffuse impurities of both types, p type and n type, acceptor and donor impurities, to make a sandwich. P type is sandwiched between two n types, or n type is sandwiched between two p types, and this device becomes very, very useful for applications. So, I talked about some of the nomenclatures, some of the geometrical parameters, some of the doping parameters. So, essentially we have three parts, three units or three terminals, let us say. The symbol is like this. You have a line here, a line here, a line here with an arrow, and these are the connecting points. These are the connecting points from where you have those leads coming out, and this one is definitely base, this one is collector, and this one is emitter. And this is NPN transistor. This is NPN transistor because your arrow is like this. Arrow gives you the direction in which, if base emitter junction is forward biased, current flows. So, that should be P to N. So, if the arrow is in this direction, that means this is P and this is N, and therefore, this is also N. So, it is NPN. And for PNP, it is a reverse, you know that. For PNP, the arrow will be like this. So, once again, this is base, this is emitter, and this is collector, and this is PNP. So, the guiding principle was, in the normal operations, this base emitter junction is forward biased. That is the guiding principle. And now, let me also add what happens at this base collector junction. The other junction is at the base and collector. This here PN junction, or here this is base, this is collector, this is PNP. So, this is P and this is N. So, this is base collector junction. So, what happens here? Base collector, how do we connect that? So, in normal operations, base collector junction is reversed bias. I will just tell you why it is so, because the whole mechanism is based on this. So, how do I bias this transistor? There are two PN junctions, both have to be biased. One is to be biased forward biasing and other is reversed biasing. Okay. So, that biasing in this fashion can be achieved in several manners. One possibility is that you take this transistor, and this is the emitter side. I am talking in terms of NPN, but the same discussion, same description will be valid for NP, for PNP also. As I said earlier, all the arrows will be inverted and all the polarities of the battery cells will be inverted. So, if you have this transistor, then let us take this as the common terminal, 0 grounding, okay, and then this base and this is base emitter junction should be forward biased, and remember this is NPN. So, this is N and this is P, and this should be forward biased. That means this should be at a higher potential than the emitter. So, that is the forward biasing. So, if I bring it here, put a resistance and then put positive of the battery with this, right. So, that this is at a higher potential as compared to the emitter. So, the base emitter junction is forward biased. and then base collector junction should be reverse bias. So here is the base and here is the collector, and this has to be reversed bias, and remember this is N, this is P, then this is N. It has to be reversed bias. So this N side should be at a higher potential than this P side, and this is at a higher potential than this emitter. So this should be at a higher potential than this emitter voltage. Okay, so you have to add positive of the battery here, like this. So now, and this should be strong enough, this should be large enough so that this is reverse bias, because there can be a current drop across this resistor and that can actually reduce this voltage. But this voltage should be positive and more than the potential that is dropped here. You remember, in forward biased PN junction, the voltage appearing across this PN junction, in a forward biased PN junction, it has a certain value, because after that current shoots exponentially. So it's like this, that current voltage characteristics. So you have a voltage after which you really cannot go, and for silicon it has to be less than 0.6 volt or so, that knee voltage, etc., etc. So that drop is there, so take care of that, and then this should be reversed biased. So that much cell should be here. Now this is okay, this is fine. So this configuration is known as common emitter or common emitter mode. Why? Because there are two parts of the circuit, clearly you can see from this diagram. This is one part, this is another part. And this part of the circuit, you can call it input side, and this part is output side. Right, and this emitter is common to both of them. For this circuit also the emitter is coming into picture, for this circuit also emitter is coming into picture. So it is common emitter mode, and many of the applications which we will be dealing with in this course will be in this mode, common emitter mode. You can also have other modes, common base mode for example. If you try to connect in common base mode, then let me draw the transistor in this fashion. Okay, so this is the transistor, and because I want to make all my voltage etc. below the symbol, that's why I rotated it by 90 degrees, and this is the base, and this is NPN transistor. So this is N, and this is P, and this is N. So base emitter, this is base emitter, base and emitter, this should be forward biased. So if I take it here, then this should be at a higher voltage, this P should be at a higher voltage, and this N should be at a lower voltage. So if I take it from here and then take a resistance, I should put negative of the cell here and positive of the cell here, and then connect. So this will ensure that this emitter, which is N type in this NPN transistor, is at a lower voltage as compared to this base, and this is forward biased. On the other side, this should be reverse bias, this base collector should be reversed bias, and this is N. So this N should be at a higher voltage as compared to this, and so if you put a resistance here and a battery here, this should be positive here and negative here. Okay, you can call it ground, you can call it ground, and so on. So this is common base mode, right? Then you have some nomenclatures for the cells and the currents. These are the cells, these are the batteries, these are the voltages that is used for biasing. For these you have certain symbols. Here in this diagram, this is emitter and this is collector, and this side is that collector side. So this voltage difference is known as VCC. V and then double C, twice C in the subscript capital. And this one, this voltage which is here, that is written as VBB. Why BB and why VCC? This is emitter is common to both. Emitter is not mentioned in this nomenclature, and this collector side is connected to the collector, so it is CC, and this side once again the emitter is not mentioned, and then it is connected to base, so it is VBB. And with a single C you can write VC, that is the potential of this collector. So this potential as compared to this 0, so that is VC, which is in fact same as VCE. So normally people do not use this, normally people use this, and similarly VB will mean the potential here, this will be written as VB. So these are the kind of symbols. Here if you write, this is base is common, so we won't write B here or here, and this side is collector, so this will be written as VCC. Whereas this is emitter here, this is emitter here, so this voltage difference is written as VEE. So they are just nomenclatures, this is how. Then current. Since it is forward biased, you will have a current, and that current will go from P to N. And so if the current is going like this, this current has to go through this. Now this current is written as IE. And then the current should enter in this PN junction, current should enter here, goes from P to N. So this current goes here, it enters here, this is IB. And then any current that is here in the collector, that is written as IC, and the arrow mark, this arrow is like this is IC. Okay, remember this is reversed bias, and then the current will be of this type. So these are the symbols, and if this is IB, you can see that this is just a series circuit, and so the current here should also be IB. And similarly, if this is IC and this whole thing is series, so you should have an IC out here. This IB is like this. Right? This current, the current which goes in this direction, that only goes through this and then reaches here. Similarly, the current which goes like this, that only goes and reaches here. So it is like this. You can apply Kirchhoff's junction rule at this point, and you can see that IE is equal to IB plus IC. Here also the same story here also. This is emitter, so this current will be IE, this current will be IE. And since this is PN junction, so the current will go into P and then N in this junction. So you will have IB here and then IC, okay, then IC. So what you see, this IC current must have gone from here, IC, because this is one series and this IE is one series. So this IE will go like this. So once again you can see that this IE is equal to IC and plus IB. So the same IE equal to IB plus IC is there. So this is about the names and the directions of current and the polarities of biasing cells or biasing batteries, biasing voltages. It is like this. And now I will be talking of mechanism of this current, how the charge carriers move at these junctions to give this kind of current, this kind of configurations. So, let us look at that. So, let us consider a transistor, NPN transistor in common emitter mode. So, I have this transistor, and then I have a resistance, then this is P and this is N. So, this should be at a higher voltage, and so it should go like this. Always use this basic physics to remember things. It is not that I have to connect this positive that side in NPN, in CE mode, etc., etc. This has to be forward biased, that is it. So, that will decide what kind of polarity should be here. And this is N, so this should be connected to again positive of the battery. So, this is our configuration. This is our CE configuration. Now, what happens? This is the most important physics involved. This emitter and this base, this N here and this P here, this emitter base, this is emitter and this is base. This is forward biased, and this N is heavily doped, emitter is heavily doped, and the base is lightly doped and is very thin, So, what happens if you have a normal PN junction? If you have a normal PN junction, you have depletion layer, P side, N side, and then you forward bias it. So, what happens? Because of this biasing, the potential barrier decreases, and because of the large concentration gradient, majority carriers from both sides diffuse to the other side. Okay? So, if you have a large number of electrons here, free electrons, conduction electrons, large number of conduction electrons here, small number of holes. So, the majority carriers, once that barrier is reduced, they diffuse to this side, which we call minority, remember, minority carrier injection. Because here they are majority, but when they diffuse through this depletion region and come to this side, if these electrons come to this side, they are minorities. This is P side. Electrons are minority carriers. So, a lot of minority carriers are injected from this N side into this P side. And what do these electrons do? Here you have large number of holes, So, if this length is sufficient, if this space is there, if the electrons take considerable time traveling from this to this, in between many of them will recombine with the holes here. They will combine with the holes here, and that electron hole pair will be vanished. And if an electron hole pair combines, the electron is coming from here, but the hole which was there for all that charge distribution, charge neutrality, electric field, potential, this battery will maintain all those things as a function of time. So, if this hole is filled, a new hole should be created somewhere to maintain that charge balance. And that happens, some electron hole pair will be broken here, and then that electron which is extra, that electron will flow through this. The electron will flow through this, and therefore current that will contribute to this current I, which is going here. Okay? And of course, once the electron is here, it will go through this and complete the circuit, and that will contribute to IE. I is equal to IE plus IH. So because of these electrons, because of these conduction electrons, you have the current. And similar thing will happen for these carriers. These are majority carriers. So these holes will diffuse on that side and they are minority here. So once again minority carrier injection. Then some of the holes will recombine with these electrons, and then similarly you will have electron coming from this side to make that charge balance, and the whole current is like that. Here what happens at this junction? This is a general thing that generally happens in a PN junction diode. Here the extra things are, one, this emitter, this N-type, this emitter is heavily doped. This is one. And this P here, this base, is lightly doped. This is one thing. And the other thing is this base is very thin, and after that you have this another PN junction. Which PN junction? Base collector. Base collector junction is right there. So now the situation is something like this. First let us think of this first junction. This is emitter, which is N-type, which is heavily doped. That means a lot many electrons there. Many electrons are there, very small number of holes. Remember, Ne into NH is Ni square, okay? Ne into NH is Ni square. So if one is very large, the other is very small. That is one. And on this P side, on this base side, let me show this base here. It's not this big. So this is that base which is P-type. It is lightly doped. That means even the majority carriers don't have large density as compared to this. In P-type H, these holes are the majority carriers, but it's lightly doped. And therefore, in this IE and IH, it will be dominated by the electrons. It will be dominated by the electrons, and this current which is there, this current will be primarily because of this electron injection here. So this IE which is here, this IE is primarily because of those electrons which are injected. So electrons are going this way and current is going that way. So that's one thing. Second thing is base is very thin. So that means this is thin, and for these electrons to recombine with these holes, you need a certain time. They come and they move, and then they combine with those holes. But if you don't allow sufficient time, most of them will not recombine in that thin space. So that's why it is made so thin, of the order of micrometers, that these injected electrons, they just cross through. They just cross through this base region almost without recombining, or a very small fraction of that will recombine. If it recombines, remember this is biased, so you have this positive and this negative here. So then this mechanism will take place. The current will go like a PN junction. Whenever there is a recombination, wherever this electron comes here, and then in P region it recombines, then you do have a current, corresponding current, just like this. Okay, so this IB, the current in this base region, that is because of this recombination, but that probability of recombination is very small because of this low thickness, because of this fact that base is very thin. So the result is recombination probability is small. And this finally tells that IB is small. Most of the electrons do not see what is here. They just reach this second junction. There is a second junction. This is your collector side. So most of the electrons which are injected from here, they cross this P region and reach this depletion region here. You have a depletion region here at this junction, you have a depletion region here at this junction. So once they reach this depletion region here, these electrons, what kind of biasing is here? This is reverse biasing. And these electrons are minority carriers. Okay, these are minority carriers. For this junction, this PN junction, electrons are minority carriers. And the electric field is there to draw these electrons. So your electric field in reverse bias is like this. So the direction of current is like this. And this electric field that helps the minority carriers in making the reverse current, and therefore all these electrons which are crossing and reaching this depletion layer here where you have this field, they will be drawn towards this collector and will go to that biasing battery which is there. This is P, this is N, so you should have positive here, whatever resistances and all that. Okay, it's connected here, but anyway the potential difference is there, right? So what is the picture now? The picture now is this emitter has injected lots of conduction electrons into this base, but the base region is very thin. These electrons cross over that base region and reach the depletion layer of this base collector junction. And that collector is waiting for these electrons with a strong electric field to attract. And these electrons are attracted and these electrons go through that collector, and that makes the current IC. Okay, so this is IC. Since the electrons are going this way, your current is in this direction. And the electrons are going this way, some of them which recombine, corresponding to that you have a small current in the base, and that electrons are going this way, so the current is this way. The same picture, IB and then IC, and this IB will be like that, and then this IC will be like that, and IE will be equal to IB and plus IC, so that picture. So this is the mechanism. So you have to very clearly understand that the current in the transistor circuit is crucially, and that is why the transistor is made in that fashion. It crucially depends on the thickness of this layer, the sandwiched base layer, and the level of doping, the concentration of doping in emitter and in this base, and then of course the reverse biasing and forward biasing and all that. So this is how the current goes. All right, so once you understand this mechanism of how current goes from the emitter into the base, and how most of it goes into the collector and part of it goes into this base circuit, then we can go ahead and discuss what kind of biasing, what kind of resistances will give what kind of output currents, collector current and things like that. So how the parameters of transistors will be defined, and how the biasing will control the currents, and what we can do with this kind of situations, all those things can be discussed once we understand this physics of injection of carriers from emitter to base, and then why that thin is made so thin. It's made so thin because we want most of it to get transferred to the collector side, and only small part should go into the base side, and all those things. So that physics we have discussed today, and our next lecture will be on studying the effect of biasing, magnitudes of biasing, how much biasing we should give, and what kind of applications we can generate from that.